So I'm going to try and simplify adjectives associated with Frobenioids. So it's really Frobenioids and let's say Frobenioid elements, morphisms of Frobenioid elements, etc. Okay, so we've seen what a Frobenioid is, and I'm going to set up some notations. So we're going to take X to be the Frobenioid, the model Frobenioid associated to some monoid functor, the principal divisors, and the divisor class morphism functor. Okay, and then we're going to have it sit over S, which we're going to call, which is going to be f of phi of x. Okay, so this is the elementary Frobenioid here. So this is what we're going to call, this map we're going to call ELT. This is going from the elementary, from the Frobenioid here to the elementary Frobenioid. And so, again, so if we have a morphism in here, this will go to f ELT here. Okay, and then so this is all going to be, this is all over a base category, which we're going to denote d of x. So recall that if we have a morphism in x, so for so we're going to have these objects, so v of y, alpha of y. So these are going to be objects of x. Then we can look at a morphism here, phi, and the morphism has 4 components, right? It's going to have this map here. So this is going to be the morphism on the base. This is the divisor. There is the degree. And then there is this unit element here. And this part here is what we'll call the elementary. Okay, we'll do it with phis here. So this is the elementary part, these 3 components here. Okay, and maybe it doesn't hurt to write it out again. The morphism must satisfy the following. Okay, and this is as of so we have phi of x, and then v of x. Okay, so again, we look at we're looking at the monoid group. Okay, so we're looking at the monoid here, associated to the domain here. All right. So that being said, I guess I can start with the one morphism predicate. So these are just some things that are used to talk about morphisms of Frobenioids. So again, we're going to have phi. Where can I write this here? It's going to look like f phi, div phi, deg phi, u phi. Okay, So this is going to be a morphism, and then there's various conditions we can impose, and a lot of the time we'll impose them on the elementary part here. Okay, so here's a condition. So the condition would be that this part here, the elementary part, looks like star star 1. Okay. What this is saying here is that since this third component of the elementary part is the degree, this is just saying it's degree 1. Okay, so it's a degree 1 map. So then so this is the condition. So this is the meaning, I guess. And then this is the name that is given to it by Machizuki, and he calls this linear. Okay, so if you have a degree 2 map, this would be degree 2, etc. So let me do double bars here. Another thing you could do is you could say this can be the first component can be whatever you want. This component here could be 0, and the second component could be whatever you want. So what this says is that there's really no associated divisor to the morphism, so no associated divisor. And what this means is, so the term here that he uses is isometric. And apparently this comes from Archimedean Frobenioids. So here's another condition. So we can just keep going like this. So we can take an isomorphism. We can say that the base is an isomorphism. Okay, and so this is exactly what it looks like. It says the base map is an isomorphism, and so you call this the base isomorphism. Okay, similarly, if you were to put the identity here, you'd get the base identity. Okay, there's some more complicated things that we can do, but first let me talk about pullbacks. So here's another condition you can impose. So recall that if we have categories like this, where we have a functor here, let's call this one F. Okay, we can look at a diagram here in X. It goes down to something in S, and we can look at a functor. Okay, so we're actually going to identify. So we will identify X S Y T with the functors they represent, hx, hy, hs, ht. So these are the kind of like the functor of points. So in this situation, we could take a functor. Okay, so take a functor here, and this could be to whatever. And so, for example, this could be one of these guys here. And what we can do is we can pull this back. So we can look at G composed with F. And so that goes from X to S to whatever. So this goes from X to whatever. Okay, and so this thing is the pullback of G to this category. So this is an X. And now it makes sense to ask the following. Okay, so if we're using this identification here, well, we can take Y and we can base change it by pulling back T and pulling back S here. Okay, and from this we'll get a natural map from here. So this is the natural map induced by, so this is a natural map. And so if so this exists, so this is a natural map from phi. Maybe we shouldn't call this phi, maybe I'll call this phi tilde. Okay, so then, so the definition. So if phi tilde is an isomorphism, then, so this is Yoneda again. Okay, so if this is an isomorphism, then we say that, phi is induced by pullbacks. Okay. So maybe I'll underline it. So this is another condition you can put on a morphism. So let me just say okay, let me give some more. I'm going to give some more. Maybe we can go back here. So we had this pullbacks. So let me give another one. Okay, I'm just going to write some more down. One. Okay, so if you have one that looks like this, so this is what he calls a pre-step. Okay, if we have one that's if we have one that's like this, one, and it's not an isomorphism, then we say that this is called a step. Okay, so I mean the meaning here is, I mean it's kind of clear, so I'm not going to fill that part in. But let me say something else. Okay, so maybe I can just put it here. So we'll say if star is primary, so that we can use the decomposition of monoid elements. If this into a products of primes, if this thing's primary, meaning it's like a power of a prime, then we say that this is a primary step or pre-step. Okay. So there's like all these combinations of words, and so I don't think it's good. I don't know. I find it very confusing to think about these words, but it's more useful to think about these. These are the combinations of conditions you can do. The other conditions you can do are well, we'll see. The other conditions you can do will have to do with phi or like the divisor. So you could say things are like divisor equivalent. Let me give an example of how we can use some of these things. So let's do like an exercise. Okay, so we'll look at the word isometric pre-step. Okay, and so how do you figure out what that means? So here you go here and you look at and we look at isometric. So isometric says it's this. So isometric means it has this form, so that the divisor in the map is 0. And then the pre-step says what? So a pre-step says that this is an isomorphism, this is whatever, and this one needs to be degree 1. Okay, so it's linear. Okay, so if we put these two together, we get an isometric pre-step, which is the condition like so. Okay, so let's do another example so we can see how these work. So we can look at a linear base isom. Okay, so linear, well, this just says that the degree is 1, and base isom means that this is an isomorphism, and this can be whatever. Okay, so then we get a linear base isom, and it looks like an isomorphism here and then 1. Okay, so notice that this thing here, a linear base isom, so note, so a linear base isom is equal to a pre-step. Okay, so some of this language is redundant. That's the kind of the point of this. All right, well, that's that. And now what was I going to do? I was going to talk about conditions on two morphisms, okay? So, okay, I think I'm out of notebook space, so I'm gonna stop and start a new thing. Let's talk about two-morphism. Predicates. So this isn't that it's a two-morphism, but I'm going to look at pairs of morphisms. So we're going to have, let's say, phi1 and phi2. Okay, so here we can look at two of these guys, and then maybe this is like f1 alpha 1 d1, and this is f2 alpha 2 d2. And so, okay, so I guess this is this elementary. The elementary part of that is this and this. Okay, so that being said, what other conditions can we do? So we can make some conditions here. Okay, so we could say that if they have the same domain and range, and alpha 1 is equal to alpha 2, so then we'll call this thing metrically equivalent. Okay, so this is the name. So let's just do some more. If f1 is equal to f2, then we say that phi1 and phi2 are base equivalent. So they're the exact same map on the base. Okay, and then if you could do the same thing but you could do it on the divisors. We could say they are div equivalent. Okay, so again, this is a morphism in D. So this is so again, the Fi are morphs in D of X. Okay, so they're morphisms in the base. Okay, and so when you have a morphism in the base, you have this contravariant functor, so it makes sense to talk about them being div equivalent. Okay, so I forgot to say the weirdest one morphism. So back to one morphism predicates, for example. So there's a very weird one morphism predicate. So let me just do one morphism predicate again. Predicate. Man, that was not good. Okay, so let's suppose that let's suppose phi is f. What else do we need? We need a divisor. We need a degree, and then we need a unit. Okay, so I'm kind of like mix and mashing notation here, so it's not very good. But suppose. Okay, so this is the weirdest condition here. So if so say phi is equal to phi1 composed with phi2 composed with phi3. Okay, and we'll suppose that phi looks like gi, and then we don't really care what happens here. Oh, actually we do. No, let's not even talk about this. Okay, so suppose this. Okay, if it looks like an isomorphism. So like I'm just going to write down the forms of the elementary parts. Or it looks like a composition like this. So this is the craziest condition. I have no idea how to think about this. But I found out recently that so after trying to learn all this, you actually don't need this for the whole interuniversal Teichmuller theory because we don't need, because we're only going to be working with model Frobenioids, and I guess somehow you can work around this. I didn't really understand that. So, okay, so suppose we have all these things, then this says that phi2 is an isomorphism. Okay, so this is some crazy condition. So this is a definition. So this is a definition. Okay, so we let this be here, and suppose suppose we have a decomposition for phi. Okay, for any decomposition like this, if it has the form like this, then we automatically know that phi2 is an isomorphism. Okay, so this is the condition that phi is a coangular morphism. Let's say coangular, which is this crazy condition. Okay, so I got that out of the way. I've talked about these things. So one morphisms, I talked about two predicate morphisms. I have not talked about conditions on objects. Okay, so conditions on objects. Then we need one object predicates too, but okay, I guess we can start with two. Okay, so here's a simple one. So, given two objects, if v of x is isomorphic to v of y, not giving the explicit isomorphism, then we say that x and y are base isomorphic. Okay. So notice that I wrote v of x and I'm not viewing it as an elementary Frobenioid or something. Okay, so I think that's the only one I wanted to talk about. You just kind of do this type of thing again. Do we want to talk about functors yet? Okay, so let's talk about one element predicates, one object. Okay, so what are some of the things you can say? Well, okay, so this one's kind of important. So if x is equal to v of x alpha of x, and this is in our Frobenioid, if for all morphisms like this, phi okay, so for all phi like this, if the elementary Frobenioid looks like isom 0, 1, then this implies that phi is an isom. Okay, so if this condition holds, so whenever we have one of these, if it looks like this, then it's an isomorphism. This is what we call okay, so maybe this if should go on the outside. This is what we call isotropic. Okay. All right.